Hi everyone, welcome to our paper on ODIN, Automated Drift Detection and Recovery in Video Analytics. My name is Abhijit Suprem. I'm a PhD student at Georgia Tech. We will first talk about video analytics and the concept drift problem. We will then cover the ODIN system architecture. Next, we will examine each of ODIN's components in detail. Finally, we will provide experimental results. Today, cameras and video data is ubiquitous. There are numerous applications from traffic management to human and event surveillance, safety management on a factory floor, for example, or autonomous driving. In each case, video analytics takes center stage of the production workflow for data processing. Over the past few years, several DBMSs have been proposed for video analytics with a focus on speed, accuracy, or a combination of both. Most of these DBMSs use ML models for the analytics task, be it object detection, classification, or identification. The ML models follow a standard model of static distributions, where the DBMS assumes prediction, training, and testing data all come from the same distribution. However, prediction data changes over time, and the distribution of the live prediction data is unlikely to match the original training data. This is an example of concept drift. An ML model approximates a decision boundary for classification, in this case between blue circles and red diamonds. When the distribution changes, the approximate decision boundary is out of date and needs to change. This will reduce performance of pre-trained static models that do not account for the changed decision boundary and so have not updated themselves. The solution, which we implement with ODIN, is to dynamically adapt to drift. Our approach, then, is to tailor models to different distributions in prediction data. These distributions can be represented as clusters. To do this, we need three tasks. We need to identify clusters as and when they appear. We then need to create a specialized model for each cluster. Then we need to find the best fit model for any new data point. ODIN automatically adapts to changes in distribution by addressing those tasks. Drift Detector identifies changes in the prediction data. Model Specializer creates specialized models for different clusters. Model Selector chooses the best possible model for a data point. For our experiment, we use the BDD, the Berkeley Deep Drive dataset, which contains 100,000 dashcam videos under different conditions, like morning, night, rainy, or foggy. ODIN is 6 times smaller and faster than a pre-trained static model while delivering 45% to 50% higher object detection accuracy on BDD on various clusters. Now we will cover ODIN's components in detail. We start with the drift detector. The drift detector clusters images and videos on content by extracting image-based features. Features are extracted with the CNN. Since they are high-dimensional, we need to project them to lower dimensions, because otherwise it'll suffer from the curse of dimensionality, which makes clustering high-dimensional features difficult. So we seek to project features to lower dimensions. We do this with an autoencoder. An autoencoder compresses images by first encoding them to a lower dimension and reconstructing them during training. As long as reconstructions are accurate, the autoencoder is functioning because that means it can store the most important image features in the latent space. Different types of autoencoders have differing performances. A standard autoencoder is poor at latent encoding. This is evident in the holes we show here for MNIST on the very left. The holes indicate regions of the data space that the encoder has not modeled. A variational and adversarial autoencoder, the two on the right, both of which try to smooth the latent space, work much better. The adversarial autoencoder yields the best results. What we use is a dual adversarial GAN, which combines two adversarial losses and a reconstruction loss. The DA GAN is constructed using ResNet blocks. The DA GAN includes the encoder and decoder of a standard autoencoder. It uses a latent discriminator from an adversarial autoencoder. It also uses an image discriminator from a generative adversarial network, or GAN. GANs are useful in creating realistic images. In our case, we want higher quality reconstruction, not necessarily realistic synthetic images, because the higher quality images would indicate that the latent representation of the GAN is working as intended. The first adversarial loss, the latent discriminator loss, focuses on the latent space to match it to a distribution. Here, the matched distribution is a normal distribution, which smooths the latent space. The image discriminator makes sure that the image has high fidelity. The third loss is a standard autoencoder reconstruction loss, to make sure that the reconstruction matches the input. A trained DA GAN will project frames to lower dimensions. Frames with similar features are closer together and form clusters. These clusters are still relatively high-dimensional, so most of their data is at the edge of the cluster, per the curse of dimensionality. So most points in a cluster appear within a band around the center. We call this band the delta band. It is a high-density set of points, where high density means greater than 50% of points in the cluster. Distributions are compared on the delta band using the KL divergence. With KL divergence, the Kullback-Leibler divergence, we can compare up a prior and posterior distribution, where the prior is the existing clusters and posterior is the live data. But once drift detector identifies a cluster with DA GAN and the KL divergence, ODIN uses Model Specializer to create new models. Our starting model is a YOLO v3 model. Each specialized model is a tiny version of YOLO v3 with only 9 convolutional layers. ODIN creates a specialized model for each cluster identified by the drift detector. During prediction, ODIN uses Model Selector to identify the best fit model for a point. Since each model is associated with a cluster, Model Selector is actually comparing a data point to a cluster or the cluster center. During our experiments, we tried 3 model selection policies. The unweighted KNN method uses k-nearest specialized models based on distance to the cluster centers. The weighted KNN also uses k-nearest models, but weights them on their distance to the data point. The delta band selection policy checks which delta band the data point fits in. It then uses that cluster's model. With the detector, specializer, and selector, ODIN can process frames. Our UDFs are YOLO models, so we perform object detections. With detector, ODIN checks if they are from known clusters and uses selector's delta band policy to retrieve the correct model. If they are from a new cluster, selector falls back to the weighted KNN policy, since a model for the new cluster might not exist yet. To evaluate ODIN, we ask the following question: whether drift detector is effective at identifying drift, whether the specialized models are effective compared to a static baseline, the performance of each of the selection policies. We also do an end-to-end evaluation of ODIN in presence of drift, and we test ODIN with aggregation queries on the BDD dataset. We compare DA-GAN inside the drift detector against state-of-the-art novelty detectors, as well as the standard autoencoder and adversarial autoencoder. On both MNIST and CFAR, DA-GAN performance is 30% better than the recent state-of-the-art. It also performs 5% better than an adversarial autoencoder in identifying drift. For the model specializer, we compare a specialized YOLO tiny model against a static large YOLO model, and against a YOLO model trained under the student-teacher approach. The difference between YOLO Lite and specialized as follows. The specialized model is trained on the detected cluster itself using Oracle labels. The YOLO Lite model is trained on the cluster using the output of the static large YOLO model as a training signal. The specialized YOLO model is around 50% better than the static YOLO model on average. On night data, it is 2 times better than the static model. For the model selector, we compare 3 selection policies of the unweighted KNN, weighted KNN, and the delta band. Both weighted KNN and delta band policies are 50% better than baseline across all subsets in BDD: the night, the day, the rainy, the snowy. On night data, both are 2 times better than the baseline. However, delta band is faster since it uses a single model, compared to K models for the weighted KNN policy. For the end-to-end evaluation, we run ODIN with all components and provide BDD as a stream, one subset at a time. We start with rainy data, then add day data. We then add night data, and finally snowy data to the stream. These are the cluster labels on the plot below: beta, alpha, delta, and gamma. ODIN's overall accuracy is 1.5 to 2 times better than the baseline. It is also 6 times smaller and faster on our object detection UDF. For other UDFs, these performance metrics may vary based on their construction. We then test an aggregate query with ODIN. The query we show here is to count the number of cars. ODIN is useful here because we need to run an object detector across an entire dataset with different types of features. Compared to a static model, ODIN has 50% higher query accuracy on counting cars. Since trucks are larger and less common in BDD, they are easier for the static model, so ODIN only sees a 7% higher accuracy. Since ODIN uses tiny specialized models, it is also 6 times faster than the static model. In this talk, we have presented ODIN, a drift adaptive system for video analytics. ODIN uses 3 components to ensure high accuracy under concept drift. ODIN's drift detector uses a dual adversarial GAN to detect clusters in the data space. Then the model specializer creates specialized models tailored to each cluster. Finally, model selector finds the best fit model for any data point. ODIN is 6 times faster and smaller than a baseline approach with YOLO for object detection UDF, and twice as accurate. Thank you very much for your time. We would like to acknowledge our sponsors for their support.